All right, Chemistry 3101. Where we left off was looking at this problem, 10.16, and I said, take the time to draw the second resonance contributor. So I'm just going to put in the curved arrows here, and we would end up with something that looks, some arrows that look like this, I guess. And so our second resonance contributor is going to look like this, except now we have the double bond in this position, and we have our radical over here. Now, after you do the halogen abstraction of the first radical, you're not going to produce a chiral center. So there's nothing to consider there in terms of stereochemistry. So we'd end up with this product. And then the second product that we're going to get, you can see that you are going to form a chiral center. So let me just draw this in here. So this, I'll move that arrow out of the way there. So this carbon is a chiral center here. And so for that one, since you pass through a radical, which is trigonal planar, you end up with a racemic mixture of this one. So this is going to be racemic. Yeah, racemic. There we go. All right, so now we finished that problem. Let's wrap up today by looking at section 10.10. This is the last section of new chemistry. And this explains the reaction that we learned way back in chapter 8. In chapter 8, if we had, an alkene and we wanted to do an anti-Markovnikov addition of HBr, we used a peroxide, and that would give us anti-Markovnikov addition. So we're going to explain that reaction now. So you remember Markovnikov and anti-Markovnikov addition. There's nothing really new here. But in order for us to understand why we get an anti-Markovnikov product using peroxides, you have to cover radicals first. And so now that we understand a little bit about radicals, we can take a look at this radical mechanism, which provides us with an explanation. So let's take a look here. It says, when the reaction is initiated by thermal homolysis of the peroxides, which initiates the formation of a bromine radical from HBr. So that's really just kind of a spiel for saying, okay, if you take your peroxide, so remember you have HBr and an organic peroxides, the first thing that happens is that the peroxides are going to break apart to give you a pair of radicals. And the reason why is because it doesn't take much energy to break that bond. So we end up with a radical, and then our radical can react with our HBr, and what you end up forming is a bromine radical. Okay, you form a bromine radical. And so it's this bromine radical that is going to react with our alkene. Let's take a look. So when the bromine radical reacts with the alkene, there's two possibilities, aren't there? If you have an unsymmetrical alkene, it could react like this, okay, and give us this radical intermediate. Or if I just redraw the radical, just kind of an abridged version of it, like this, it could also react like this. Theoretically, it doesn't, but it could. And that would produce this radical. But you see there's a big difference between the two, isn't there? The one that's in black is a secondary radical, and the one that's in red, or in the red box, is a tertiary radical. And so this provides us with the explanation as to why we get anti-Markovnikov addition. When we do anti-Markovnikov addition, we end up with a more stable radical because this radical is a tertiary radical. Whereas if we do the anti-Markovnikov addition, we end up with this secondary radical. But remember, that's only the first step that we've drawn, is the bromine addition, or the addition of a halogen. And then what happens is we do a hydrogen abstraction in the second step, and you end up regenerating the bromine radical. And so the carbon radical, after it abstracts the proton, I'm repeating myself, it forms a bromine radical, and it propagates the chain reaction, or the radical chain. So this is a chain reaction overall. So if we take a look at this, it says most of the radicals in solution at any given moment are going to be the bromine radical. So a combination of them is typically what we're going to have for our termination step. So if we go back a couple of slides here, again, just repeating myself, this is going to be our initiation. It involves two steps. Our propagation is here. It's going to involve halogen addition. So we'll put here bromine addition. followed by hydrogen abstraction. So these are the propagation steps. And then finally, our termination. Again, it could be any two radicals coming together, but this is the greatest probability, is that two bromine radicals come together and form a bromine molecule. So there you go. So that's the explanation. Now, if you're wondering, why does this reaction work if we do HBr and peroxides, right? That works. But why can't we do HCl and peroxides? And why can't we do HI and peroxides? Okay, this does not work and this does not work. Well, there's a good reason why neither of those work. And the book gives us quite a lengthy explanation, but it involves thermodynamics. Okay, so I'm just going to highlight the word here. Thermodynamics is what is involved. So if we think about the first step of propagation, so if we think about the first step, okay, first step, which is going to be the radical addition. So radical addition, okay? And then the second step, which is the hydrogen abstraction. So we'll just put here H abstraction like that. What we can do is we can evaluate the thermodynamic considerations for both of these steps for the reaction with HCl, with HBr, or with HI. All right, now I'm not going to go into as much detail as the textbook does, but I'll kind of give you the Sparks Notes version of it. So what happens is, if we look at the first step for the addition of HCl across the double bond, so the first step is going to be the chlorine addition. What happens is that the delta G is going to be negative at a low temperature. So we get a delta G for this, which is going to be negative at low T. So that's a good thing. That means the reaction is going to be spontaneous. Now, if we look at the delta G for the first step of bromination, or sorry, I should say HBr addition, we get the same thing, that delta G is going to be negative at low temperature. So that's also good. But then when we come to HI, it turns out that our delta G for this is going to be positive. And so that is why we cannot do the addition of HI across a double bond. The first step is not spontaneous, so it's not going to happen. And so this is why this process does not happen whatsoever. So this gives you a big no as to why we do not get addition of HI. So that explains why this is not going to happen. Now, if we look at the second step, if you look at the delta G for the hydrogen abstraction, when you do the reaction with HCl, it turns out that your delta G in this case is positive. And so that gives you an explanation as to why this reaction will not work. Sure, the first step is spontaneous, but the second step is not. So this explains to us why we cannot do this reaction, the addition of HCl in peroxides. Whereas if you look at the delta G for the hydrogen abstraction with HBr, in that case, it turns out, oops, I'll use my black pen, that your delta G is negative. All right. And so it turns out that it's only with HBr that our delta G is negative for both the first and the second step of propagation. Again, both of these steps are propagation. But again, HBr is the only one where both steps are going to be thermodynamically favored, and that's why we don't do anti-Markovnikov addition of HCl or HI. Now, sometimes we can form a new chiral center, right? Like if you look at the anti-Markovnikov addition of HBr across this 2-methyl-2-butene molecule, you end up with a chiral center. Well, remember that the intermediate that you pass through is going to look like this, because the first step is bromine addition, right? The bromine is going to add to an sp2 hybridized carbon. So is there going to be any differentiation as to which side it adds to? The answer is not at all. You form your radical here, but the bromine could be coming out of the page like this, or it could be going back into the page like this. So to designate that it could be either one, sometimes we put a little squiggle bond like this, which means it could be going forward or backward. And so you're going to end up with a racemic mixture. In this case, you would get a racemic mixture with this molecule. Oh, I forgot to mention this point here. If the starting alkene contains a stereocenter, then of course you'd get a pair of diastereomers or a mixture of diastereomers. So let's take a look at this question here. This is 10.20. It says predict the products of each reaction. In each case, be sure to consider whether a chiral center is being generated and then draw all the expected stereoisomers. So here's what I recommend doing. I recommend drawing the mechanism of the first step of the propagation, which is going to be the bromine radical addition. So remember, it's anti-Markovnikov addition. So the rich are going to get richer, but they're richer in bromines, not hydrogens. Maybe I shouldn't have said that. That might be confusing. But anyhow, so what we're going to end up with is this intermediate. So let's just pencil in the intermediate, which is going to look a little something. Oops, do an extra bond there. There we go. So this is going to be our radical. And is that radical going to produce a mixture of stereoisomers? Heck yeah, because you're going to have a chiral center. So after the hydrogen abstraction, you're going to end up with two compounds. You're going to end up with one where the methyl group is going to be going down. And if I just copy and paste this, so copy, you're also going to end up with the one where the methyl group is going to be going up like that. So you end up with a pair of enantiomers. So these are enantiomers of each other. And then for the next one, are we going to get a chiral center? Well, let's see. If we draw our bromine, we draw our bromine radical like that, we're going to get anti-Markovnikov addition, right? Why? Because we're going to form the most stable radical, which looks like this. Okay, there we go. And then after the hydrogen abstraction, you can hopefully see that you're not going to form a chiral center. So there's no chiral centers in this molecule. And there you go. Put here no chiral centers. Like that. All right, so that covers the entire chapter, all of the new chemistry, and that brings us to section 10.13. And so, like I told you earlier on, I showed you this exact example a few minutes ago where I said the only time that chlorination is going to be useful is if you have a substrate that's really symmetrical, like cyclohexane, or let's say you had cyclobutane or something. Sure, chlorination will work in that case, but if you have anything that has got more than one type of hydrogen in it, you're better off to go with bromination, right? And of course, if we did a bromination, you could treat it with a hindered base, and you could make the Hoffman alkene, and you could hit it with an unhindered base, and you could make the Zaitsev alkene, right? And that's kind of where we're going with this. So if you think about it, you know, once you form your alkyl halide, you can do SN2, right? SN1 reactions, SN2, or you can do elimination, E1, E2, etc. Okay, and so does anybody know what this is here? This drawing is here that I put here. It's not a joke. Anybody know what that is? I just copied and pasted it off of Google Images. Yeah, exactly, right, Katana? It's Pandora's box, okay? So really what we've done in this chapter is now you can start it with an alkane. This is something we've never been able to do before. You can just start with an alkane as your starting material and make all kinds of cool products from an alkane. Is that crazy or what? And so it really does open up Pandora's box. And not to get too far ahead of the game, but that explains why chapter 11 in our textbook, the next chapter we're going to start it on Thursday. It just deals with review of chapters 7, 8, 9, and 10, because you've learned so much synthesis now. And now that you open up this, this box with being able to functionalize an alkane, you can do a lot of interesting chemistry. So what are the main things that we covered in this chapter in terms of new reactions? I think the main one would be this one here, the bromination of an alkane, right? Where the bromine is going to go in the most substituted position. Then we also covered allylic bromination with NBS, and we went over the mechanism, part of the mechanism, I guess. Then we spent quite a bit of time on the mechanism of anti-Markovnikov addition of HBr, and I explained to you why the reaction doesn't work with HI or HCl. It's a no-go with both of those, and I went over the thermodynamic considerations for both of those. And that covers all of the new chemistry for this chapter.